Greetings. Let's generate some microwave signal today. We're going to start with our ADF4351 board. That board can be found on Asian sites like AliExpress for around $20 plus minus a few dollars. I think it's a good expenditure considering what it does. There are a few things I'd like to mention. Well, the first thing is that this board does not have any memory. So we need to configure the chip every time we power it up. And in order to do this, we need a microcontroller that's going to send data onto the data port here, which is a serial port similar to SPI. And for doing so, I've put together this little board. It's a little 8-pin microcontroller. It's a PIC12F683. That is simply routed to a 2x5 connector, and I programmed this chip, of course, to send the right configuration words to the chip to set our frequency to 3408 megahertz, of course. So that's what it takes, really. It's not a lot, but it has to be created. Of course, eventually I will share the firmware written on this PIC microcontroller for everyone to have a look at, of course. I'll put that on GitHub sooner or later. But for now, let's look at the few changes I have made on the board to make it work better. The first thing is that I've disconnected this onboard oscillator. This oscillator is used if you don't feed in an external reference, and you have to add a jumper, a 0-ohm jumper here, and disconnect the one here, which disconnects this oscillator. But even more than this, you need to put a jumper here so that you can inject your 10 megahertz external reference into the circuit, but you need to remove, like disconnect this oscillator. Why? Because I found out that it still generates a tone. It leaks through. I could clearly hear the main tone, but there was another tone right next to it, a few hundred hertz, and this was the culprit. So I just, use hot air and lifted up a couple of the 4 pins, and now problem solved. Another change I did is that by default, the board does not send RF out. There's a chip enable CE pin that needs to be connected to 5 volts in order for the chip to work. So instead of having to send the signal here on the board, I could have done it with this little board, but I instead decided to add a pull-up resistor to 3.3 volts. And this is what I do here with the brown component. I think it's just a few, like 4.7K or 10K ohm will be sufficient. And it will keep the board, always running. That's unless you want to shut it down one way or another. You can use that pin. Of course, you can always force a low here, even though the resistor has been added. Another change I've made is to replace the capacitor here. It's a 10 microfarad capacitor, ceramic capacitor, but I did not know what the maximum voltage it was set to. And my guess is it was probably a 6 volt or 10 volt capacitor. And this board is normally fed with 5 volts. So there's no way you would put 12 or 13 volts onto this board and expect that filter capacitor to be able to withstand that voltage. So I just removed the old one and installed a 25 volt 10 microfarad instead. It's a multi-layer ceramic capacitor. By the way, the regulator, the 3.3 volt regulator can take up to 15 volts. That's its maximum rating. So at 13, 14 it will be fine. It is hot. It becomes quite hot. You can't leave your finger on it for too long. But in the world of electronics, a regulator that runs at around 50 Celsius or a little higher is okay. It's okay. This part can run up to 150 Celsius. So at a what we consider hot level, hot for the fingers, it's still okay. So that change gives me the ability to feed it with 12 or 13 volts. Will I ever have another regulator that sends 5 volts? I don't know. We'll see later how much of a requirement having 5 volts is versus having 12, which is the standard voltage sent everywhere on the project. So that is pretty much the extent of the changes I made. I realized today that I am stuck with two output connectors. One is out plus and the other one is a complementary output, out minus, for a differential signal. Of course, we're going to be using only one, so we need to terminate the second one with a 50 ohm termination, and this does impact the level of the output we'll be using. If you remove the termination, it will lower the output level somewhat. Not a lot, but we can still see it. So it's best to have it terminated, and besides, it avoids leaking everywhere. At those frequencies, the smallest transmission line can become an antenna if it's not properly terminated. And I may decide eventually to simply remove that connector by blowing some hot air and adding a 50 ohm resistor right there, just a 50 ohm termination or 51 ohm between the two pads, and that will do it. It will terminate it properly. Okay, so that's the extent of what I've done on the board. Now let's make it work. Okay, I've hooked up everything for the first test. The intent of this test is to verify that our 3.4 gigahertz synthesizer, when sent into an ERA2 mini-circuit ERA2 amplifier, it's just a small MMIC that I mounted on a PCB and I fed supply to it inside. Use this to generate harmonics, and that the output will have the 10.224 harmonics that we want in a sufficient amplitude to be usable for our LO output. There's no filtering anywhere, so we're going to get the other harmonics as well. We're going to get the fundamental out, and then the second harmonic, third, maybe, and fourth and fifth, which we're going to see in a minute. This is all fed by my 10 megahertz OCXO reference. Now everything is connected up to 12 volts. So the thing is up and running, and the green LED indicates that the system, the synthesizer, is locked to the external reference. And then for demo, I can disconnect the external reference and you'll see that we're going to lose lock. Gone. It doesn't put out the proper frequency. But if I reconnect the 10 meg, the synthesizer locks again. Okay, so we're ready. Now let's turn our attention to the spectrum analyzer, which is going to look at what's coming out of this thing. So we're looking at the spectrum output of our synthesizer plus ERA2 amplifier, and I'm extracting also the IF of this spectrum analyzer, the IF signal. We can listen to this. Once we stop the sweeping of the spectrum analyzer, it becomes just a regular receiver, if you like, and it can listen up to 22 gigahertz, the maximum range of this spectrum analyzer. So I'm extracting the IF, and we'll be listening to this a little later into a receiver. See how clean the tone is. That gives us a good idea of how clean the LO is as far as usability for our sideband or CW modes. Okay, so I've captured a few plots, a few screens, and let's go see them. So here's what the spectrum analyzer screen was displaying. It's a wide shot, a capture of the frequency spectrum from 3 gigahertz to 20 gigahertz. And what we see here are obviously harmonics of our 3 gigahertz signal. This is our fundamental at 3.4, 3408. And it's really hot at plus 12 dBm, plus 13. The reference level here on the top is plus 20. Okay, so plus 13, and we won't need that signal, obviously. We're not interested in the 6800 megahertz signal either, the second harmonic. We're really interested in the third harmonic, the 10.224. This is our signal of interest. But if we keep going, we see that there's another one at 13.6 gig, and then there's another one at 17 gig or something like that. So these harmonics, along with these ones, will have to get filtered out. We want only the 10 gigahertz signal, and we'll have to amplify it, of course. So a few stages of filtering should do the trick. So that's a wide shot. Looks good so far. Let's see when we zoom in even more. This is a 100 kilohertz zoom in of our 10 gigahertz signal, 10.224. The signal shows at minus 12, minus 13. So we'll clearly have to boost that signal and then, as I mentioned, filter out. And so what do we get? We get a pretty clean signal, no major skirts here in the 0 to 5 kilohertz. That's what we have. So very good signal. So we're above the noise generated by the synthesizer by at least 10, 20, 30, 40, 50 dB and more. So that's pretty good as far as noise content. There's only one spur here in the plus minus 50 kilohertz. They're actually at 30 kilohertz apart from our carrier. These are more than 40 dB down, so they shouldn't bother us at all, especially because we're doing narrow band communications in the 0 to 5, 0 to 6 kilohertz bandwidth. So these are too far to bother us. And they may even not bother us anyway, other than if we look at a waterfall, just a small line showing, on either side of the waterfall. So it won't really bother us. I'm pretty convinced of that. Let's zoom in even more on the signal to see, if is there anything here that we should be worried about? And the answer is no. The signal is very clean. These are AC components, 60 hertz, 120, 180, 240, and so on either side. This leaks in, probably from the power supply I'm using. And of course, in a portable situation with batteries, these would not be there unless we pick it up from the air, but it'd be surprising. Disregard these, and we concentrate more on the tone itself. I think we have a winner here. It's more than 50, 60 dB down before, the skirt becomes a little wider in terms of noise here. So I think in the end, it'll be a very clean signal, but the way to convince ourselves is just to listen to the tone produced by this thing in sideband or CW and see how clean it is. So let's listen to the 10 gigahertz signal picked up by the spectrum analyzer. The spectrum analyzer's IF, it's at 3 megahertz. I'm sending this into my FT817 radio. So I'm tuned to around 3 megahertz and we'll be listening to the tone at 10 gigahertz and we'll see how clean it is. I bring in the tone. So I'll move the frequency so that you can hear different frequencies. See how stable it is? It's not moving at all. This thing is very stable, and it will be a very stable system once everything is put together. So to me, this sounds really clean. I don't see any issue. So it will be a good source for decoding narrow band signals. I'm pretty convinced of that. That's all for now. See you later. 73.